Hello. Okay, this is another type of applications of first order differential equation, a simple electric circuit model. Alright, we just introduced simple electric circuit model, and it's mainly in electronic or physics. Okay, physics. So let's say you have a circuit with an inductor. Right, you have a circuit with inductor, and then you have a resistance, right, resistor. So then there is a direct current supply. Right. Direct current supply is not alternating it's not an alternating source. Alright, it's not alternating, it's direct current. So okay, we study this because this is simple, right? So then we go through the coil, and the coil will generate the magnetic field, right? There is an energy here, right? Energy produced. Then this is a resistor also, right? The resistors. So then we always assume that this is a perfect without any EMF or any resistor, internal resistor inside there. For maths, we talk about perfect models, alright? So for this, we have electric supply, right? The voltage, the electric supply is the same as the voltage of the voltage across the inductors, which is I di dt. Alright, I di dt, sorry, is L di dt, the inductance. So I, the inductance of the inductor. Alright, and resistor, you have resistance, right? Yes or not? So then plus with IR, V equals to IR, right? V1 plus V2, right? The total supply equals to the energy loss, right? So L di dt plus with IR. So this is the models, right? If you look at this, this is actually a differential equation. Alright, it's a differential equation. So if I rearrange this, it will be look like L di dt plus with IR equals to the electric source, right? So for this case, this is a constant because this is a direct current. It's not an alternating current. So that's why we said simple electric current. Alright, so let's see how to derive the formula for the current for this circuit due to time. Alright, so I introduced again, as just now we said that this is E, and the voltage supply is the same as the voltage as the energy loss here, right? Which refer to the Kirchhoff law. So as the voltage will drop across this, so this will be your I di dt, alright, I di dt. Add with the voltage drop here, right? So plus with IR, which is equals to E, where E is a constant, alright? E, the resistance is constant, right? It's constant, and the inductors, the L, alright, the L di dt, the L, the inductance also will be constant, as L, the R, and the voltage supply is a constant. So means that there is the change between the current and the time, right? So the current change due to the time. So means that in this case here, so we have L di dt according to Kirchhoff law. So if the voltage supply, so this will be the total voltage here will be the same as the voltage for the voltage supply here, right? So L di dt plus IR is equals to E. So how to solving this? So as you look at this, is actually something like a first order linear differential equation, which you have form of Pxy equals to Qx, right? It's a first order linear differential equation. As if I rearrange this, you can see that this is somehow like L di dt, Ri, right? This is just like dy dx, right? And this is your y, right? And Px will be your So this one must make sure that this is 1, right? Before, so I have to derive such that before I using the concept of first order linear differential equation, so I have to write in the standard form here. So means that I must add up with R over L, right? Divide everything by L, so I have I and E over L. This is all a constant, all right? So if you compare with that, this is like dy dx, di dt plus with px y. Y is I now. Y is I now as equals to E over L, right? So from here, I'm going to using the concept of integrating factor in solving this equation to getting the formula for current. So how is it? As you still remember that the first step is standard, okay? First step. So the second step will be you need to write in the form of the integrating factor, which will be Vt, right? Vt exponent integrate. This is your Pt here, right? Dy dx plus with pxy. So this is your Pt, so which is R over L. And remember that R over L is a constant, all right? R over L is a constant. So as we integrate the constant, we can take out the constant, right? We can actually taking out the constant. So where we can rewrite this to be exponential R over L integrate 1 dt. So then we have E R over L integrate 1, we have t, right? So this will become your integrating factor, right? Integrating factor for this model. So now I'm going to multiply this into the equation, right? This equation that already in the standard form. All right, let's multiply into the equation. So multiply E R over LT into the equation. So we have E R over LT di dt plus with R over L E R over L T I equals to, so we multiply the E R over L T, right? With each term, right? So E over L. So if you see that, I have multiplied everything with E R L. So the fourth step, if you still remember, by using integrating factor, I can rewrite these two into a one term, right? Two term, we write into one term. So which is y here, the y in this case is I, and this is your integrating factor, right? Integrating factor. So if you're using the concept of product rule, the differentiation rule, u, right? U di dt, right? Plus with I, v, differentiate exponent. This is a constant, right? So you just multiply, differentiate this, you're getting R over L E, R over L T. And you have E over L, E R over L T. Right? I'm going to generate formula now, which I'm going to integrate both sides. Okay? Integrate both sides by with respect to t. So R over L T I dt. And for same thing here, I divide E over L E R over L T dt. So integrate and the same time differentiate, so you get back the integrand. So L over R T I. So which is equates to E over L is a constant. Alright? E over L is a constant. So I've taken out the constant and you have E R over L T dt. So let's sum up everything. So okay, now what I can do is I want to continue derive this. Okay, right? So we continue integrating as integrate E R over LT. It's just like you integrate e2x dt, right? A constant with t. So you take e2x over 2, right? Yes, not over 2. So for this, you just take, let's look at it here. So we have e R over LT. So this is a very good derivation. So E over L and E R over LT, right? R over LT divided by R over L, just like E2x over 2, right? So, okay, now add a constant C, right? A constant C after you integrate, right? So this is a general solution. So as you can see that E R over LT I is the same as E over L, and this one when you go up it will become then R over L, right? L over R, sorry. So E R over LT end up with C. Okay, finally I have E R over LT I equates to E over R, E R over LT plus with C. This is a general solution, but I have to write I in terms of T, right? Before that, I can find the constant C first, right? So as a knowledge, so you have to know that initially, before I switch on the switch, right? Before the switch is on, there are no current, right? There are no current in the circuit, right? So it means that initially when T is 0, the current is considered to be 0. Alright, so we have to understand this. So we can substitute the current with 0. The time is 0, current is 0. So this whole thing will become 0, right? As e to the power of 0 is 1, but I is 0, so everything becomes 0. So E over R. And e to the power of t power of 0, so you're getting 1 plus C, which implies C is negative E over R, right? C will be negative E over R. So, very simple. So let's continue the derivation, right? Okay, let's continue, and we know that C is negative E over R, right? So then we substitute E R over LT I equates to E over R, E R over LT plus with C. C is negative E over R, right? Negative E over R, and I can divide everything by E to the power of R over LT. So means I divide by E over R, and then I'm getting I. And for this, I divide by ER over LT, divide by ER over LT. I will getting just E over R minus with E over R. Divide, right? So divide by ER over LT. So finally, I can just factorize E over R as a constant, E over R. Then in the bracket, I have 1 minus with, 1 minus with. For this is 1 over ER over LT. So you can rewrite it as E negative power of E power negative R over LT. And this is the formula for this circuit, the current, right? So it means that the current is depend on the time, right? So this is the formula of the current for this circuit. After the derivations, so this will be the formula. Alright, let's look at the problem that relate to this model. Alright, let's continue with this problem here. Alright, let's look at this problem here. So this problem is a case that for a simple electric model, circuit model, so which is a LR series circuit. Alright, the inductor resistance circuit. So an electric circuit contains a power source. Power source is your E, right? E, and a resistor with a constant resistance R, a constant, right, resistor. So and an inductor with a constant inductance of L, right? L, E, and R is a constant, and the current IT in the function, right? So it's depend on time. Amperes flow through the circuit is given by this equation, which is the equation just now that I write, L di dt plus Ri equals to Et. So I have to carry out the derivation. Okay, that derivation you should do in finally to getting this formula, right? So this is the application of first order differential equation by using integrating factor. So then this question now is asking us to solve. If the resistor is 12, inductance is 3, and the current is 0 when the time 0, right? It's according to what I'm derived just now, where when the time 0, we haven't switched on the circuit, right? Switch on the switch, so the current is 0. So find the current if the power source, right? The power source is 6. So let's look at how to solving this. So as the question already tells us that the E is 6, right? 6. So it's a battery, right? The voltage of the battery. And the resistor, the resistance of the resistor is 12 ohm, right? 12 ohm and 6 volt. And for the inductance is 3 Henry, right? Doesn't matter about the units. So for mathematics, we just want to calculate, right? So then according to here, we already have the formula, right? But you have to show your working just now when during your derive. Okay, you derive. So now you can just plug in the formula, right? Plug into the formula. So the battery can be changed, can be 12 watt, can be 18 watt, all right? So this is the formula, standard formula for the simple LR series circuit. So which is 6 divided by R. Resistor is 12, right? 12. So 1 minus E to the power negative R over L, right? R over L. 12 over 3, right? 12 over 3 is 4T. So finally, I have the formula for the current for this circuit, for this specific circuit, which the power source is 6 voltage and the resistor is 12 and the inductance is 3. This can be changed, right? But now this is based on these cases here. So and the question saying that what happened to the current after a long period of time, right? So the current will change, right? During time is 0, during t is 0, right? During t is 0, this will be 0. 1 minus e power 0 is 1. Then the current is 0, right? So when t is 1, there is a current. When t is 2, there is a current, right? When t is 3, there is a different current, right? Means the current is changing, right? So the question is asking, what happened to the current after a very long period of time? Long period of time means the value of t getting bigger and bigger, or we can say that the value of t is approaching infinity, right? So then we have some knowledge for limits, right? As you learn in your semester 1. So as t approaching infinity, let's look at here, because this is a constant, so we just observe at this thing here. What happened, right? So as t approaching infinity become very big, I want to know that what is happened to e power of negative 4t. So let's think intuitively. So which we can rewrite this to be 1 over e to the power 4t, right? Since this is negative, we can write as 1 over e to the power 4t. What happened when t approaching infinity, right? As t approaching infinity, the e power of 4t, right? The e power of 4t, which is for this one, it will be approaching infinity also, right? Because as the value getting bigger and bigger, so exponent to the power of infinity, you are getting very big value, right? So the impact of this will be, as this getting infinity, but this is 1 over infinity, means that a number divide a very big number. Of course, this whole thing will be approaching 0. Means that finally, after a very long period of time, we usually will use this as a mathematical way to explain. As after a very long period of time means the limit as t approaching infinity for the current. So what happened, right? So it's actually to calculate the limits of the currents. So 1 over 2, 1 minus e negative 4t, right? So as I said that the value of e negative 4t will be approaching 0. So as this approaching 0, this whole thing Okay, we can set this to be 0. So 1 over 2 times 1, you were getting 1 over 2 ampere. This is the limiting current. Alright, means that the maximum current, right, in the circuit will be 1 over 2 ampere. Right, this is to make sure that the circuit will not burn, right? It will be stabilized, the current is stabilized finally by this mathematical proven formula, right? The current will be stabilized. Alright, that's all for this video. Hope you understand about the simple electric circuit model.